Hey, YouTubers, Tazman here, bringing you another T4zzTeaches programming logic. And in our last episode, we learned a whole lot about data types and how the memory works and binary and all that fun stuff. And we're going to kind of expound on that a little bit today. But first, we're going to kind of go into some more things that we need in order to do computations and stuff like that with our programming and stuff. Because, well, let's face it, if you have a program that outputs the exact same thing every time and really doesn't, like if I had a program that just says hello world, which is the common one, after maybe 2-3 times, I'm bored of it. I'm not running it anymore. So we want a program that's going to give value. And for that, we're going to want to be able to get user input. We're going to want to be able to do computations. We're going to want to be able to, evaluate things and so on and so forth. So in order to do that, we need to have some more knowledge on our basic stuff. And we're not going to get into the input just yet, but we are going to focus on operators and the different types of operators that you use in programming. And there's actually various types. We have our standard ones that we all love and know from mathematics. We have, your addition, subtraction, division, and multiplication. Actually, that's not how you do multiplication in, we just do an X, right? Well, in computers, the reason I did kind of a star shape is because in computers, we do use addition normally, the same sign. Subtraction, we use the same sign. Division, we actually use the forward slash to signify division. And then multiplication, instead of the X, we use the asterisk or the star. There's also one other that kind of uses what we look like division, but it's actually the percent symbol. And that's called modulus. Now the modulus is basically when you're doing division and you have a remainder, that's what the modulus is. So, if I'm doing division, I say 2 divided by 4, obviously this goes in it goes in 2 times 4. So everything works out perfect. But if I'm doing, say, 2 divided by 5, well, now we're going to have what we call the modulus. So we're going to have this. It's going to stick out 1, and then we could, this is where we do our decimal, and then we add, what is it, a 0 here? It's been a long time since I've done this. Now we have 2 into 5. No, that ain't right. Anyway, we end up with 2.5. It's been a long time since I've done long division on paper. So anyway, but that's what we end up with is 2.5. 2 goes into 5 2.5 times. All right, so this right here, if I were to do this as a modulus, so if I were to do 2 divided by 5 as an integer, all I get back is 2. If I did 2 modulus 5, I would get back 5, right? So this is actually really good because one really handy thing this allows you to do with a computer is simply if you divide something by 2 and you get 0, so we could say any number. If we said, let's say x is a number and divided by y, if it equals 0, whoops, I meant modulus, x modulus y. If it equals 0, we know that that was an even number, evenly divisible by 2. Actually, let's change y to 2. So we do that. So if we take any number, modulus 2, where's it, 2 modulus any number? We'll figure it out as time goes on, but you kind of get my understanding. So if we do a modulus with 2, if we get back 0, we know that that is an even number. So it's a really quick way of finding that out. But we can also, do all our other type of math, addition, subtraction, multiplication, and that's all in division. And then we have the modulus to tell us what the remainder is in something. Now, in programming, it also does the order of operations, and of course it will always do it from, I believe it does it from left to right. However, there are things that take precedence. So anything in parentheses is always executed first. Now, if we have multiple things in parentheses, this and this, plus that and that, it will always do this set of parentheses first, then this set of parentheses, then it will do the addition. So it will do the order of operations. So the order of operations in programming is your parentheses always go first, then it does multiplication and division in whichever order. So it doesn't really matter if division's first in the line going from left to right, it'll do division first. So these two are kind of interchangeable. Let's just do that for interchangeable. And then we have our subtraction or addition, subtraction, just since we have the positive thing there. And those are interchangeable too. So those are your operators in general for doing your math type stuff. So let's go ahead and add in a new page real quick. And we're going to get into what we call our relational operators. R-E-L-A-T-I-O-N, relational. If I misspell anything, I apologize. I'm not the greatest spellerer in the world. So relational is going to tell you basically the relation between two things. So if we have x and y, right, x and y, we use relational variables to tell us the relation between those. So, and these are greater than, less than, is that right? No, that's less than, greater than. And then we also have the less than equals to and the greater than equals to. So these can evaluate to, you know, is x greater than or less than or greater than equal to y? So if, for example, this is 5 and this is 5, and we said this, right? Then we're saying, is 5 less than or equal to 5? Well, this is true. Whereas if we say 5 and 4, right, then we say here less than, greater to, or equal to, this one's false. Because 5 is not equal to, and 5 is also not less than 4. So, but if we reverse that and did 5 or 4 less than equal to, well, actually, you know what we should do? Hold on, I'm going to just back it up a little. We'll keep our 5 where it is. Let's do to there, one more. Right there. So now if we say 5 and we say greater than or equal to 4. So here, obviously, this is true because it is greater than 4. It's not equal to, but it's greater than or. That's an implied or right there. And therefore, that is true. Okay, so we have these type of variables, or we could just do it with this, where now if this is false, because 5 is not less than 5, it's not greater than 5 either. So we could do this, where this is stays false because the equal to is not there and stuff. So this is our relational operators. So we have the less than, the greater than, the less than equal to, or the greater than equal to. All right, so let's move on to our next one. We have quite a bit to cover. I'm really hoping we actually are able to get it all in. All right, so next we have our equality operators. E-Q-U-A-L-I-T-Y. So our equality operators are going to be ones that tell us if one is actually equal to another. And in programming, generally we use a double equal sign to do the equality comparisons. And to do the opposite, the not equal to, we use the bang or the exclamation point on our equal sign. So the reason we do this is because if I say 5 is 5 equal to x, and let's say x up here equals 3, right? What this is actually, it's better to do it the other way. Hold on, let me see. I messed up. I wanted to do x first. Let's go maybe here. Nope, a little further. Almost. There we go. So, oops, we don't have our other equal part, but that's okay. So what I wanted to say is, okay, so we have x up here being 3, right? And if we say x equal 5, well, this is the assignment operator in programming. So now what we just did here is we actually took x and we turned it into a 5, right? We don't want to do that. So in programming, we would say here, for example, once again, x equals 3, and then we say x equals 5. And then the computer is going to know, oh, wait, I'm trying to compare these two to see if they're the same. And it says, okay, here's 5, x is equal to 3, 3 is not, therefore this whole statement is false. Right? So, and then of course we can also do this with the inverse. We can use the not. And if we said this same thing here, we could say x not equal to 5. And here we would say 5 is this, right? X is equal to 3. Is 5 or is 3 not equal to 5? And this would result in true. So these are your equality operators, and we'll use those throughout program also. This also is kind of known as a negator, kind of negates the equals, and you can use that. We'll learn also that you can also negate entire things. Like if we said, like we had a whole thing here saying not, in parentheses, 1 plus 3 kind of thing. This is saying not 1, 3. So we're 1, 3 or variables or whatever. This is actually really kind of hard to understand right now, but as time goes on, we will definitely understand that. And then next we have one called our logical operators. And these are ones, we're not actually going to cover them all. We're going to cover basically some of them. So what we know these in English is and or. So when we're comparing something, or we're trying to, well, yeah, I guess comparing something or evaluating something, we might say, I want ice cream and cake. And therefore someone knows that I want both ice cream and cake. If I said I want ice cream or cake, that means I want one or the other, but I don't want both. And that's the same type of thing in programming. We could say, say that, if this and this are true, and usually you use this with true and false, you're evaluating something to see if it's true or false. So if I said 5 equals 5 and you do 2 ands and 2 ors usually, and the or is actually the pipe symbol, which is the shift backslash, or it's the key right above the enter key, and is usually double ampersands. So I said 5 and then I said maybe 5 equals, I messed up there, equals 3. This whole thing's going to evaluate to false, because this needs to be true, which it is, and this needs to be true, which it isn't. So we have a true and a false situation there. This to be true, this entire thing to be true, both these components have to be true. Now it's the opposite with the or. If we did this exact same thing with the or and said 5 equals 5, and then do 5 equals 3, holy cow, can you hear all that banging? So this one is true. This one is false. Or what? Yeah, this one's still false. F-A-L-S-E. However, we want this to be true or this to be true. We don't care if both are true or both are false. Although if both are false, then the whole thing's false. But in order for it to evaluate true, one of these have to be true or both. Both could be true because still one of them is true. All right, so these are kind of our operators, and we'll probably cover in depth more and everything. If you don't understand this all really well, rewatch the video a couple times, and once we get into programming, getting into the programming, play with it, experiment until it clicks for you, because everyone's different, and things that might make sense for one might not quite make quite enough sense for another. But if they play with it enough, all of a sudden one time it'll just bing, okay, now I get it. And we'll get into some other things like XOR and all. There's a lot of different, there's also a NOT, which is kind of also the bang symbol and stuff. But these are kind of the ones we need right now to just understand basic computer logic. So the next thing I wanted to talk about was, remember we were talking about how we had, for example, let's just come back down here. Okay, so we had, we were talking about our binary values, right? And we were talking, I kind of messed up in my video and I said, oh, and if I want 128, I do 8 ones. Well, that wasn't right, because if we look at that, if we say 1, 2, 4, 8, 16, 32, 64, and 128, right? If I want the value 128, then I would just put a 1 here and a 0, 0, 0, 0, 0, 0, 0, because this is 8-bit world, right? That's all that exists. If I had all ones here, which would be 256, right? Because it's double that. So if we added 1 plus 2 plus 4 plus 8 plus 6 plus 32 plus 64, and then the 128, then we would get 256, which is 1 higher, and would put a 1 here, and it would negate basically all this stuff back to zeros. And the computer, because this is the carryover, even though this is 256 now, 256, wait, is that right? Yeah, 4, 4. Yeah. Even though the value is 256, our world only knows about 8-bit. Therefore, we think we're back at 0. And this is going to kind of, I'm going to kind of explain something about this. Now, you'll also remember that we talked about that an integer, for example, an int is a positive / negative whole number, W-H-O-L-E, whole number. Well, if we're saying that 128, if we have all this marked and we have a 255, I believe it is, then we didn't have any negative numbers there. How do we represent the negative numbers? Well, before I go showing you what we do and how the computer handles that, I want to show you another thing. I kind of mentioned, we have our primitives like int, double, bool, and char. However, int actually kind of has a separation. So it actually kind of splits up. So you can actually int, the class int, or maybe we'll say class whole numbers here, represented in computer, can actually be a byte. There's a type called byte. There's one called short. Of course, there's the int. And then there's one called long. So a byte, which is what I wanted to talk about next, just to help understand something. A byte is the smallest integer type we can actually hold, and it's just 8 bits, just like a real byte. So this is taking our world just to an 8-bit world. So here we have a byte, which is basically just 8 bits, right? And then the short, I believe, is like 16, int is 32, and a long might be 64. I can't remember. It might also depend on how your operating system is set up. If you have a 32-bit operating system, then if it actually represents a long, that might be the 32 pushing. I'm not exactly sure how that works. I can research that if you're really interested. But what I wanted to point out with getting into negative numbers, I'm going to use a byte because I think it's going to help us the most. So, for example, we have here 128, which is actually, our value 128, which is when we have the 1, 0, 0, 0, 0, 0. Everything else is 0 in our world. So let's really quick, we're going to go look at, let me just grab this here, grab that one. Look, I prepared. And then our numbers here, right there is good. Did that have, okay, that has something. Okay, so here is our basic world. Here we have, oh, I have to click on the right one. Yes. All right, so here we have our binary values. Here we have our decimal values, right? So in binary, and we're just going to take a 3-bit world, and the reason we're doing 3-bit is just because the way binary works is if I have these values here, if I say I want a 3-bit world, I can do 2 to the n because we're doing binary, so it's 2 to the n, which is how many bits we want, so 3, and from that we get 8, right? If we do 2 to the 4, we get, what is it, 2 times 2 times 2 times 2, right? So our numbers go up exponentially. So to keep this fairly easy and fairly small, easy to understand, we're only going to do a 3-bit world. And as you can see here, we have 0 through 7, which is our 8 digits. We can't go any higher than that. That's important to remember, that this is only a 3-bit world. So as we learned in our last episode, that we have our binary here. We have the value 0 is 0, 0, 0. 1 is 1, because there's 1, 1. So that goes there. A 2, well, we have a value 2, so 1 goes there, and that leaves none left. So we have a 0 there. 3, we have 1, 2, right? So we have a 2, but then we have minus 3 equals 1. So we still have 1 left over. Therefore, we have the 1 in the 1's place. 4, we have a value of 4. 5 is a 4 and then a value of 1. 6 would be a value of 4 and a value of 2. And 7 would be a value of 4 plus 2 plus 1. So we have 1, 4, 1, 2, 1, 1. So that gives us our 8 digits. However, you'll notice we don't have any negative numbers here. In order to have negative numbers here, we have to do something. We have to make it so we actually have negative numbers. So let's go ahead and blank this stuff out, and we're going to talk a little bit about how they came up with ways of doing this. And there's actually 3 ways, and the third one we're going to learn is actually the best one. So the first one is called Signin Magnitude, S-I-G-N and magnitude, M-A-G, mag, N-I-T-U-D-N-E. So Signin Magnitude. And the way this works is basically said, okay, well, since we only have a 3-bit world here, we need to have a way easily to understand what is going to be our positive numbers and what is going to be our negative numbers. So they simply said, okay, let's look at, we have zeros here. Let's call those positive and these ones negative. Oh, that was kind of rough. And the way that works is then this is 0, this is 1, this is 2, this is 3. But then we need to have a, this is negative 0, this is negative 1, negative 2, and negative 3. So it's not very intuitive, and you have to know, it's not even intuitive for a computer. But we just basically break it in half, and if it has a 1 there, that's a 0. So as you can see here, 0, 0, so that's 1, or 0. This is a 0, 1, so that's 1. That's a 1, 0, which is 2, and 1, 1, which is 3. So that's where those numbers come from. But 2 issues kind of really exist. One is hardware doesn't like the idea of a negative 0. So this has a huge thing with these 2 zeros that make it less intuitive and kind of a pain in the tushy. So they kind of said, nah, that's not necessarily our best way. So they went ahead and scrapped that idea. And they came up with another one that they now called 1's complement. O-N-E, 1's complement. C-O-M-P-L-I-M-E-N-T. 1's complement. And this kind of worked the same way as the other one, but what they decided is we're just going to invert the bits. So we just flip the bits. So here we have a 0, which is 0, 0, 0. So the invert of that would be 1, 1, 1. So therefore, we have a 0 as our positive, but then unfortunately we have a negative 0 still, right? So we take 1 here, which is 0, 0, 1. We flip the bits, we get 1, 1, 0. So now we have 1 here, and if we look down here, we have negative 1 here, right? Continuing on, we have a 0, 1, 0 for 2. We get 1, 0, 1 for negative 2. So here's our negative 2, and here's our 2. Then finally, we have a 0, 1, 1 for 3, which means we have 1, 0, 0 for negative 3. So this kind of worked, and it kind of worked almost the same as the other one. However, you'll notice now we have kind of a bit more structure, because we're not just adding these two together to get our 0, this to get our 1, this to get our 2. We actually kind of have a structure where we're just flipping the bits, and the inverse of whatever this is what that's going to be. So a little bit more intuitive, if you ask me. Maybe it isn't to you, but we still have that double zeros, which is very, very bad. We don't want double zeros. 0 is not a positive or a negative number. It's just a number, right? So let's go ahead and get rid of that one and say no. Then they came up with one more idea, and they call this one the 2's complement. I guess if this one wanted to work, they would have went for 3's complement. I don't know. TWO 2's complement. COMPLIMENT. If I misspell anything, I apologize. I am not a very good speller. So now the way we did 2's complement is we did the same thing as 1's complement. First we did the flip the bits. Flip the bit. B-I-T. We flip the bits, but then we add 1. This is number 2. We add 1. So let's see how this works out for us. So we take, let's just start actually with this guy. So we're going to flip number 1 here. We're going to go ahead and say 1 is 0, 0, 1. We're going to go ahead and flip the bits, which is this. And then we're going to add 1, right? So 0 plus 1 is 1. This is, of course, going to be zeros. So we have, is that right? That doesn't seem right. I might have messed up something. So we're flipping the bits and adding 1. Yeah, I think that's right. 1, 1, 1. No, that's not right. Yeah, actually, okay. I think that's right. Let's just go through it. Maybe I messed something up. So that's our number 1. Let's just keep going and just see if it works right, because I think it is. Because if we do 0, for example, we go 0, 0, 0, and its inverse is 1, 1, 1. Then we add 1 to that. So a 1 and a 1 is 2. We don't have a 2 place. 2 in binary is a 1 and a 0. Therefore, we put the 0 down. We carry the 1. Same thing here. We get a 0. We carry the 1. Same thing here. We get a 0. We carry the 1. Now, remember what I said about earlier, that we're in a 3-bit world. This is a carryover, and it's ignored. Therefore, in this world, 0 is 0. 0 is both the negative and the positive. So that works really good. So let's just try these others. Just make sure I didn't mess something up somewhere along the lines. But let's go ahead and do 2, which is a 0, 1, a 0. And we'll go 1, 0. 1 is the inverse, or the flip the bits. And then we add 1. So here we have the 1. If it's right, we're going to get a value right there, right? I think we did it right. So this is 2. 2 is represented like that. That's a 1. And that's a 1. So, okay, I think I did do it right. So that's our negative 2. Do the same thing with 3, which is right here. Or that's our 2. Here's our 3. So we're going to go 0, 1, 1. We're going to invert it, flip the bits. And we're going to add 1. So here we get 1, we get 0, and we get 1. So this is -3. Now you'll notice one thing, because we don't have two zeros, we actually have an extra value, right? So this ends up being a -4, which is kind of weird, but, and you'll notice here also that this kind of does the exact same thing, where everything that in the world that has the third bit, negative will be the ones and positive will be the zeros. So this actually gives us a -4. Now, one of the reasons I kind of wanted to show you this, and I'm going to demonstrate it really quick, is right here. I'm going to pull up Eclipse, and we're just doing some quick thing in Java here to kind of demonstrate this. So here we have the base package is all our base class here. If you don't understand any of this, that's okay. We're going to learn this at another point. Public stati. Did I type that wrong? I sure did. Main, and then we're going to do that. strrin. I apologize. I am not a fast typer in any shape or form. And I freely admit that. Okay, so what we want to do here is make sure I have everything right. Okay, we're good. I want to kind of demonstrate this because if you were to look in the world of a byte, which is only 127 bits, right? Or I mean 256 bits, 255-ish, whatever you want to say. Is that right? Is that what we said it was? It's so easy to get tongue-tied in this. Let's see, is this where we did it? Turn this guy off for a minute. No, it was up here somewhere. No, big mess, right? Quality, it was right here, I thought. Yeah, so we have the 128 bits, but that gives us 255 values, right? So you might think, remember what we said is if a 1 is in this last spot, the number becomes negative. And you're going to see why that's kind of relevant, and we're going to see an example of it. So we're going to take a byte, which limits just to that single byte of data. So we're going to go ahead and we're going to declare a byte, B-Y-T-E, and you don't, like I said, don't worry about the syntax here. We'll just call it my num, and we're going to assign it the value 127. And that's good. And then let's go ahead and we'll just maybe output our number, and it should output 127. So let's go system.out.println and parenthesis my num. Right, so there we're outputting it. And then so if we run this, we're going to get 127, right? Right down here, we're going to see a 127 pop up. Now, if I add a value to this, if I say my num, and then do plus plus, and this is how you just basically say my num equals my num plus 1, and then I re-output that, what do you think it's going to give us? Do you think it's going to give us 128? If you said that, you're partially right. It actually gives us -128. Why is that? So if we think about this in our example there, where's my Photoshop one? There it is. So if we look at this, turn off this guy, come here, add a layer. Add a layer. So if we look at this and we say we have our values here, go 1, 2, 4, 8, 16, 16, let's see, what was it? 32, 64, and 128. So if you remember, we said that if it has a 1 here, now in 2's complement, that means it's a negative number we're doing, right? So When we have 128, which is this, in binary, well, when we invert that, we get the opposite of it, right? So we actually get the negative side of it. Actually, I think I wrote this a little wrong, but it's because of that right there that it ends up looking like it's actually a negative number. Kind of like when we looked at our values. Where was it? Oh, right here, I think. No, I don't remember which. Now I have all these. I think I've been thrown away. So anyway, sorry about that. So that's how we handle the negative numbers. We use 2's complement. Hopefully that made sense to you. If it didn't, you know, maybe watch the video again, see if you can understand a little bit more. But remember that in order to do 2's complement, we're just basically kind of shifting the bit or inverting the bit, where we're saying we're taking, I've got the wrong there. So we're saying that in our 3-bit world, we take this bit right here and use it for whether it's positive or negative. And we take the bit, so remember for 2's complement, you flip the bit, and add 1. Whew, that's an ugly D. Add 1. And that will give you the negative number. Hopefully you guys did enjoy the video. If you did, be sure to leave a thumbs up down below. Aside from that, comment, like, and subscribe. Follow me on Twitter. Check out my other channels. I have my T4zzTeaches, or this is the T4zzTeaches. I'm used to saying this on my other channel. I have my Tazman channel, T4zzM4NN, and I have my Taz Unplugged channel. And there should be links to those all in the video description and stuff like that. So check those out. Also, you can join me on Discord. I get on there every now and then, chat with people. And you can meet up with me there and chat and such. And that's it. Until next time, I'll be seeing you later. Bye.